My name's Adrian Randolph, Dean of Northwestern's Weinberg College of Arts and Sciences, and thank you very, very much for joining us today. Welcome to this third virtual conversation for alumni with Weinberg College faculty today with Professor Omar Farha. This virtual series is meant to deliver updates on cutting-edge research from faculty experts at Weinberg College to you, our alumni and supporters. And as individuals who've really been invested in our community, we hope that you've been enjoying these thought-provoking and varied perspectives, which are really focused on the pandemic and our responses to it. So before we get started with Professor Farha, a few practical matters. First of all, if you have any technical difficulties during this talk, please use the chat function. If you don't know where that is, it should be at the bottom of your screen, just to the left of center. It says chat, the little bubble, sort of cartoon bubble there. If you have trouble, write something in there and we'll try to help you as best we can. We have folks who are monitoring that. Second, we will be taking questions for the last 10 to 15 minutes of today's session. So please submit them using the Q&A function. Now that's a bit distinctive. That isn't on all Zoom chats. Many of you are probably very acquainted with this technology. But if you see to the right of center on the Zoom window, there should be a Q&A with a couple of those cartoon sort of text bubbles. If you put your questions in there, we will try to get to them. And finally, just so you know, these and the past conversations are available on YouTube. So we will be recording this. And we will circulate the links to everyone who's signed up for this after the session. So now let me turn my attention to the topic at hand. As you may know, Weinberg College has one of the world's most prestigious and accomplished chemistry departments. Today, we're joined by Dow Chemical Company research professor Omar Farha. Professor Farha's research seeks to solve exciting problems in chemistry and materials science, ranging from energy and environment-related applications to challenges in national defense. He and his research group have created nanomaterials that deactivate toxic nerve agents. This innovation recently received a RAPID grant, an RAPID grant, from the National Science Foundation. And this grant will allow him to build upon his work to develop a chemically modified face mask that can deactivate viruses upon contact, including the novel coronavirus that causes COVID-19. Now, Omar Farha's research accomplishments have been recognized by several awards and honors, including an award established in his honor in the department, the Omar Farha Award for Research Leadership, which is really, I think, singular at Northwestern. Professor Farha has been named a highly cited researcher. This is a title that researchers get depending on the reception of their work, and his work is highly cited in the discipline and elsewhere. And he's been a highly cited researcher since 2014. Omar is also the co-founder of NuMat Technologies, the first company to commercialize an engineered system level product enabled by something called metal organic framework materials, MOFs. So Omar, thank you so much for being here with us. It's a delight.
Adrian, thank you so much.
So we're going to get right into this. Omar, I shared a very brief introduction to your research and recent applications. Can you share a bit more about the research that you and your research group do at Northwestern?
Thanks, Adrian. And let me start by saying I'm really, really thrilled to be here for this chat and to talk to our alumni and our college supporters. And before I start, also allow me please to introduce my group, the people who actually do the work. I am the spokesperson on their behalf, but they are the ones in the front lines doing all this work, all the way from the undergrads working in my group, fantastic undergrads, to our visiting scholars from all over the world. And we are so proud of that. We are able to tackle these complex problems, as Adrian just mentioned, that my group is interested in working on clean energy, all the way to also environmentally related applications, such as air and water purification, and the protection of human lives from toxic chemicals. we are able to do that because we really work under the umbrella of, at Northwestern, but more importantly, the Weinberg College, and then Northwestern Chemistry Department. What does that mean for us? Being able to work in an arts and sciences college, having the brightest undergraduates, all the way to doing our one type of research in a chemistry department like Northwestern. Let me just spend 30 seconds to tell you about the operation of chemistry department. This is a department that has about 45 faculty between tenure, research, and teaching lines. It has about 500 graduate students, postdocs, and visiting scholars, 3,000 undergraduates that comes through it. And more importantly, we have about 50 staffers. So you take that, and that's almost a university or a college by itself. That's the size of the operation, where that's why Northwestern Chemistry Department, it is where it is right now. But now, today, I would like to tell you about our work against toxic compounds. And this picture shows that these compounds have been used since World War I. And you could see from this slide here, I'm using old pictures because I want to get it across that protective gear is not a new concept. This one has been used for many, many years. And if you watch a show called Homeland, and there is a CIA agent, her name is Carrie Matheson, in the show, stopped a nerve agent attacked in a subway in Berlin, Germany. And at this point right now, you might asking yourself, okay, I joined this chat for Omar to tell me about what happened in World War I and then a Hollywood show. So what is all that has to do with reality? To tell you, if you just do a simple Google search, you will find such toxic materials have been used several times in the last few years. This is very topical. I will tell you about nerve agents at the beginning, and at the end, I want to close connecting all our learnings to how we were trying to implement what we learned against the war of COVID. So here, current technologies, it's what we used in our kitchen. So in our kitchen, you use this technology that it's called activated carbons. Its job just to filter your water in your sink or in your refrigerator. Our material has the ability not just to filter very toxic chemicals, but to capture them and deactivate them against really, really harmful materials.
So let me just jump in there and, well, I think the next slide is maybe going in the direction I was thinking of. I mean, what is the technology behind these, behind what you're doing? Because I think in some ways it's difficult for those of us outside of chemistry to understand how could something like a filter deactivate a virus like COVID-19. So what's a little bit more specifically, what's the technology?
Yeah, absolutely. As I said, the current technology, it's used even in the soldiers' masks, is really the same as what we use in our kitchens. So you could see this is really old technology. It's not specific. And with the chemicals, toxic chemicals, nerve agents, and now we're getting into the biological aspect, such as viruses, you really need to make some sophisticated technologies to be able to go after these issues. And we call them sponges because if we take one of NU sponges, it's built from metals and organics. I'm not gonna call them metal organic frameworks. Let's just call them our favorite NU sponges. And we're all very familiar with kitchen sponges, bath sponges. If you think about it, if you have a water spill and you use your bath sponge or your kitchen sponge, you could really wipe that water and capture it in these tiny holes inside the sponge. The question is, can you now program these holes to be uniform have a task, and the task is very specific to be able to go after the chemicals we want to go after, but not touch anything that is not toxic. So we want to make it very, very selective.
Could you say a little bit more then about how these sponges actually work?
Yeah, sure. I mean, let me show you one of those Northwestern sponges. So I'm showing you here an animation, and we are really diving into this animation. And you don't really need to know any chemistry, but imagine this is one of the nerve agents. Our sponges are very welcoming because we program it to be very welcoming. Then this nerve agents interacts with our sponges and it captures them. But that's how the current technology works. But our sponges, beside just the capture, they have the ability to actually deactivate and detoxify the agents to render them inactive. That means once we capture them, the soldiers or the civilians, they really don't have to worry about is the cartridge of their filter is filled or not, because we completely destroy it into something that does not harm the soldier or the civilians. So this is a nerve agent, this is sarin. And if you far away from the slides and you just squint on it, you might say, you know, the molecule, ignore what the molecules are, but the molecule on the left very much looks the same as the molecule on the right, except I am highlighting in green very tiny changes. And this tiny change in this molecule takes it from something that kills you to something that does not harm you. And that's what we want to be able to do, and do that very well in few seconds in order to protect a human life. And the idea, we work on a technology in my group, not just to be able to destroy toxic chemicals when you find them in warehouses, to eliminate them and eliminate them in an environmentally friendly way, but we also want to do the formulation to put them in their masks. And I will show you how to also coat the soldier's uniform. And that's the technology we adapted for COVID. And you'll see that in few slides, all the way to making antidotes. So how do we build these materials? Let me take you to a game, that kids build and put together Tinker Toys. I am using Tinker Toys specifically because it's been discovered in Evanston, where Northwestern University is, and that's why we're using it as an example. You go buy a box of Tinker Toys, you get all these pieces. In no time, the children can put them together simply and make, to a child who's 3 or 4 or 5, these are quite complex and sophisticated structures. So the idea in my group, we thought about, why can't we take this, learn from how we build Tinker Toys to now build more sophisticated Tinker Toys, and let's call them nano Tinker Toys. These are the metal organic frameworks, or these are the sponges. How do we do that? The idea is we want to program them. We don't want to do it like Tinker Toys, taking one piece at a time. We want to put everything together and have them assemble into the structures that we already pre-programmed to do specific tasks. So here, if you are a chemist, you might see some of those molecules and recognize them. If you are not, don't worry about it. Imagine those are just pieces of Tinker Toys getting together to make these sophisticated complexes. This is even a better picture. So how do these materials look at the end? On the left side, I'm showing you a vial of blue crystals. Imagine if your salt shaker is not white, it's blue crystals. That's how they look like. If you look at them under the microscope, you start to see these beautiful shapes and facets. And that's really what the sponge I showed you earlier, by just mixing these chemicals together, they assemble to make this more sophisticated material. Now let's go the reverse. I showed you this beautiful material, polyhedrons in facets. Now let's dive into these crystals to show you where really the action, how we could capture these agents and detoxify them. we always talk about nanotechnology. What does that mean? Because when you look at the crystals, these are almost millimeters in size. This is not nano. This is the nano once you dive into the smallest repeating unit of that particular crystal. So here, allow me just for a second to talk a little science. So you might ask yourself why these materials are better than the sponges that we use in our homes or what the soldiers currently have in their masks. You know, these, yellow or golden spheres, they represent molecules, toxic molecules, and molecules like to stick to surfaces. Let me give you an example. Right now, there is more air molecules sitting on your hands and your face than in front of you. So even currently, your face and your hands, this is the surface that your air molecule you are breathing likes to be sitting more on it than just in front of you. The more surfaces you have, the more molecules you could interact with, and the higher the capture. More importantly, we could tweak our materials in a way not just to capture them, but to convert them to something non-toxic. And that's the key component into what makes the Northwestern sponges more than just a typical sponges that you could buy currently on the market.
So how does that then, could you tell me a little bit more about how, well, first of all, I'm fascinated by the idea of the surface. So it really depends on how much surface you can generate. Is that sort of the key to how, let's say, the applications work when you apply these to materials for protection, the environment, etc.?
There is two components. If you're trying to store a molecule that you want to release it later, like let's say hydrogen in a hydrogen fuel vehicle, then exactly that, the more surface you have, the higher the capacity. But for protection, we want to do that. We want to store as much as possible, but we also want to have the function to destroy that toxic chemicals and make it into something less toxic. But let's take an example, as another sponge. So this is white. Would be something, sugar crystals or the salt crystals. In that little tiny vial, there is 1 gram of NU 1501. To put it in perspective, 1 gram of this material is exactly the same size as 1 sugar cube. We're all familiar with sugar cube, just to put it in perspective. Now, if you take this 1 gram of material and you unfold it into its original components, this is our favorite Ryan field. With 1 gram of 1501, we could cover 1.3 Ryan fields. Just imagine how much surface area is there in such a tiny, object. A size of 1 sugar cube has the same surface area inside it as 1.5 Ryan fields. And that's the trick to being able to do what we are doing right now.
That's great. So in a way, for a lay person, it's something that's folded up very, very, very small. And so there's lots of surface area. And then when you unfold it, it produces more. And I assume other compounds don't act like this. I mean, the sugar cube could only cover a very small amount of space. Fascinating.
That's right. But let me just add a little more to what I just said. I showed you here really 1 gram. 1 gram is nice for a lab like my lab to do a lot of testings. However, if you really want to commercialize such a material, you really have to make it at the metric ton. You need to scale it. It needs to be stable, and the price needs to be right. And that's why you mentioned that I'm a co-founder of a company called NuMat Technologies that is able to do that. And that's also another hallmark of the chemistry department. Besides just making things that they are cute, we make things that they are also functional and useful, that a lot of us professors have the ability to license this technology from Northwestern to be able to take it to the real world applications. You know, but also beside, I showed you that these materials are powder and we want to put it on filters. But how we get it connected to the COVID work? It's connected to the COVID work because working with the, you know, Army labs and working with the DoD, we were able to coat the textile, the uniforms themselves with our, our Northwestern sponges. This is just to show only in our group that we are able to make meters of these materials. And honestly, in the next couple years, I wouldn't be surprised to see thousands of meters of textiles coated with our sponges and being fielded to be used to detoxify agents. So not just the masks. So we want to protect soldiers from their heads to their toes, their masks, and also their uniforms that they are using. You could think about that. That's not going to be just for soldiers. It can be used for civilians. It can one day be used for the firefighters when they enter a fire and there is a lot of toxic materials for them not to just be exposed to that. So once you learn how to deal with the DoD related applications, with the hope in the future to take it to even more civilian type of applications.
I'm assuming that it's also how do you code these materials for various agents, right? I mean, how do you account for various different forms of chemical compounds that they might encounter? And that must be a challenge as well, to have that multiple of different types of things. I can see now, I think, how it could be effective for COVID, right? Because the textiles, so I assume if you're breathing through this, it would deactivate, or what was the word used? Detoxify, I think.
Deactivate, detoxify, destroy.
Yeah. Can you share a little bit more about the process you went through and the work you've done exploring this problem?
Yeah, absolutely. So let's use a mask as an example. Obviously, it doesn't have to be just this particular mask. Mm-hmm. The mask is also made out of fibers or textile. We showed that we know how to coat, textiles for the Department of Defense using our sponges. But then there is another technology that we are very, very familiar with. And a few months ago, we paid a lot of money just to have a few milliliters of it, is, hand sanitizer. Inside the hand sanitizer, there is a lot of ingredients that their job is to go to to kill viruses and bacteria on your hands. So what we decided to do when the United States had a problem with, the amount of PPEs was available to the front line workers, that we start thinking, how can we leverage what we learned for the Department of Defense and nerve agents into COVID? We know how to coat our compounds. And now imagine if we fill the cavities or these holes inside our sponges with the active ingredient inside the hand sanitizer. And this way, when you have something like a COVID, and by the way, this technology does not have to be only for COVID. This will work in any virus, because God knows 5 years from now, what kind of problems we can be dealing with. So this technology, we want it to be more general than very specific to go after whatever virus it gets. The virus comes, interacts with the mask, and the mask deactivates it. That means this is a self-cleaning PPEs. You don't need to take the PPEs to a special chamber. You don't need, so that you don't have to worry about changing the PPEs constantly. So we hope at the end of this program, and we thank the NSF for the funding that they were able to give us to be able to do. We have the right facilities at Northwestern, but also the funding helps to be able to do this work. Hopefully by the end of the program, we start talking to companies into how to scale up this kind of technology and have it ready for the frontline workers.
Yeah, well, I mean, speaking for the group, I'm sure we all would like to have one of these masks. I mean, that sounds in today's world so attractive to have something where not only are you not spreading and maybe not breathing in large aerosol droplets or whatever, but also you're actually destroying the virus. That would be terrific. So I know, we've spoken before, and I know your work a little bit. You've got lots of other things going on. Just before we get to Q&A and discuss, see what the group comes up with questions. So group, start thinking of questions. What's next for the Farha Lab? What are some other issues you may be tackling, or what's on the horizon?
Yeah, absolutely. There is a lot of environmental applications and clean energies that we didn't talk about, but all these applications, we want to try to improve our accuracy. That means it's nice that we could go to the lab and make things, but sometimes COVID taught us that if we want to go after an applications, it would be nice to know what we should make before we go to the lab and make it, in order to reduce the time to be in the lab and to get to the point making that mask that is ready for the front lines. And how are we doing that? This is how typically it's been done in labs. You have a bunch of chemicals, you get graduate students, undergrads, and postdocs, and they do try and error until they find the right materials. This works, but also in collaboration with modeling colleagues in McCormick, such as my colleague Randy Snur, the chair of the chemical engineering department. We've been working on how to use supercomputers to be able to model and predict which one of those sponges we should go make in the lab before we even go to the lab and make it. So we start with hundreds of thousands and millions of options, and we want to narrow it down to a handful. This way my graduate students and postdocs can go to the lab and make a handful very quickly, test them, and actually get to the answer as quickly as possible. So high throughput in the right meaning of a high throughput.
I got to say, I find this to be one of the most exciting things I've heard, because I think in general, using predictive analytics to increase experimental efficiency just sounds like a terrific move. I think it's really smart. I'm looking at something else. What's this?
This is just what I showed you so far, how we were able to really learn from what we made for the Department of Defense over the last 10 years and implemented to tackle COVID-related applications.
Terrific. So I want to say, well, thank you. Thank you for the slides. It's great. I don't know how the rest of you feel, but for me, being a non-scientist, it's great to speak with Omar, because he managed to explain things in ways I can understand. And I assume that means many other people can understand this. There's a question, and I'm not sure I know. It's Carryville. I don't know exactly what that's a shortening for. I don't know, but it says amazing mask technology. What is the possible timeline to market? How long? I can tell all of us are eager to have those masks.
This is an awesome question, and we are about to test. We already know how to coat these materials on the mask textile. We have done that in the lab because, now we're doing it against bacteria. And we already lined up the Army labs to test against actual COVID, because honestly, we are not set up in my group to be able to do that. I like to be good at what I'm good at. I am a materials chemist, and then we gotta send it to the biologist to be able to study it. Then there is companies know how to deal with textiles. They know how to scale up our sponges. We hope if everything goes right, and that's why I'm gonna use the word, if everything goes right in the timeline, it should be in months. But if that doesn't work, I told you that we made these antiviral masks to be general. Even if we can't use them against COVID, we all have to deal with other viruses in the future. So at least we will have a technology ready and not have to worry about the shortage of PPEs.
That's great. I'm going to jump to Kevin Ozinskis' question. Hi, Kevin. Does the nano sponge, because I had this same question, does the nano sponge material load up with the agent being filtered? And does the sponge then need to be replaced and cleaned?
No, that's a good question. The answer is no. We fill them up with the active ingredient that we wanted to kill, let's say COVID. So it's the opposite. We want to empty them. And these materials have smaller cavities than the actual what's in your mask. So, and beside we want to kill COVID, the question is, everybody now familiar? I'm sure if we ask people what's N95 a couple years ago, I am included, I did not know what's an N95 mask means, but now I know. And the question is, how can we make even N95 mask even more effective? By coating it with some of our sponges. That means we don't allow, can we take it to N99 and not allow any of the agents to go through it and detoxify? Yes, after a while, maybe in few days, you might have to throw away your mask because you emptied everything inside the mask from the active ingredient. But if you think about it right now, somebody has to change a mask between patients, assuming they have masks to change between patients. Or I just heard on the news a couple days ago that we have nurses putting their masks on the dashboard of their cars for the sunshine to kill the, the virus, and they take in turn which mask to wear that day. So how about if we give them a mask that they could wear it for a week and not having to worry about? That would be, it's not gonna be forever, but it's gonna be a lot better than what we have right now.
So there's a couple of questions about your lab and sort of how did you get into this work? How did you get involved with even MOFs or the notion of these type of nanomaterials?
When I was a graduate student, I really wanted to work in areas that it's a platform technology. That means if you want to being able to maneuver from one application to another without having to change a lot of things is very important. And once you start digging as a graduate student, what's exciting, this MOFs became on the top of my list. At that point, I did not know it's going to be one of the hottest topics. It's actually, MOFs is one of the most cited fields in the area of chemistry. But when I got into it, I did not know that. So I gambled in that way, but I got into it not for the citations of how important the field is. I got it for how useful this technology can be.
So another question here from Nicole Wallace. It must be interesting for undergrads to work in your lab. What kind of work do undergrads do? What can they do in such a complex technology, complex zone?
It's actually, I showed you, it's like Tinker Toys. It's actually not complex. That's the nice thing about making what we make. We take simple components to make very sophisticated molecules to do sophisticated tasks. But if you go to the beginning of it, it's simple components. The nice thing, I am at any given point, I have at least 2 to 3 undergrads in my group. We love that. Our undergrads publish. They never leave our group without having first or second author publications under their name. And we make them work on, catalysis for clean energy, which I didn't talk about here, or purification of water from toxic organic compounds or toxic heavy elements. So there is a lot of work the undergrads can do. Excitingly, in Chem 350-2, one of the experiments we actually test, it was developed in my group about metal organic frameworks that actually every senior and major chemistry students get to do that at Northwestern University. So that's really cool to see even our chemistry now, it's taught in undergraduate labs.
So there's another question here, which I think restates Kevin's in a way. Why would you need to change an N95? But the other mask, you said it destroys and doesn't fill up. Could you, I think the metaphor of the sponge works, except it gives us the impression that this sponge is filling up with COVID or some other compound. And I think you explained this to me before, that something different is going on. When it gets into the nano cap sponge, what happens then?
Sure. Yeah, so the main thing is, let's start with the nerve agent, what I started with. Those molecules, we want to invite them into the cavity of these holes inside our nanomaterials for our nanomolecules to be able to destroy them, not just to capture them, to be able to destroy them. However, when it goes to COVID, COVID is large, and we make our windows to our cavities smaller because we don't want COVID to enter the cavities. We want to fill those cavities with the antiviral reagent that is able to kill COVID on the surface of our sponges. And since they're only on the surface, you're not going to get the buildup of inside the cavity and clog them. So basically, your sponge cannot do its job once, or at least the deactivation part of COVID, when the inside of the nanoparticles are emptied from the antiviral components.
Got it. So I think some people may be interested too in what is science in this crisis? I mean, how is it working for you? Northwestern is in a sort of phased reopening of campus in preparation for the fall, but research opened up pretty early in May and then gradually through June. How does it look from your perspective? How is science doing both at Northwestern and then more generally, what do you see as the dangers for science maybe in the coming years given the crisis?
Let me talk about Northwestern, and I think honestly, our VPR did an awesome, him and his team did an incredible job. So kudos to Milan and his team for doing everything right and the reopening at the right time, and giving us the guidance into how to open safely instead of just open early and randomly. Mm-hmm. So they picked the right timing. Everything my students and postdocs, they need to stay safe, from masks, hand sanitizers, disinfectant is available by Northwestern with no charge. This is incredible. The safety office is doing an amazing job. I have to say, I am in my office right now, so I am very comfortable to be here. And also the way I see my students, they're all comfortable to be in the labs because we are at the right capacity, that they are safely doing the work, but also they are socially distancing inside the lab, outside the lab. The mask is required when you are in hallways, if you are in offices. It's just something I don't understand why wearing a mask is supposed to be a problem in other, and we're not gonna go into politics, that people don't just do something so simple that might save a lot of lives and bring the curve down very quickly to allow even more opening. So if you really want to take care of our economy, we need to take care of this virus. And to take care of it, we need to socially distance, wear masks, wash hands, whatever the scientists have been saying for the last few months. And we know it works because it worked in many other countries. So this is experiment already been done, and we know what the results if you do it right.
Yeah, well, I think I'm an optimist. I think the country is coming around on this issue.
Oh, I agree.
There is a question from Jim Pendleton about, and I think I alluded to this before, how is the specificity defined for the target and its deactivation process? There are many forms of virus, for example, and variants of the virus that evolved during the epidemic. So how do you make sure the reagent, I guess, is up to date?
Yeah, so sure. Thank you for the question. I always like to talk about the two areas I talked about here. So when it comes to, let's say, the nerve agents, I call our materials, we want to make, even though sometimes I call them smart sponges, but we want to make them also to be a dummy sponge in a way. What does that mean? I want it to not care if it's a VX or if it's a Serin or if it's a JD. I want it to go after it and destroy it regardless what agent it sees. So in this case, we are very successful at doing that. Our sponges will go after whatever agent they gotta get attacked with. From a virus perspective, honestly, we don't have the specificity right now And don't forget, this is an area we just started working on it as of May 1st. That's when our rapid started. So we're talking about, we've been working in this area for 3 months with the hope we did not want to make it specific. We wanted to actually go against specificity and go into generality because we don't know what's next. It could be that by the time we have a COVID-related mask, that maybe COVID problem is taken care of. But maybe next is going to be a different virus that we want our mask to be deployed ASAP, because by then we already have the technology.
Well, I assume, I mean, you referred to before, this work is going to have to engage with people in other disciplines to be able to make sure that whatever the reagent material compound is in the mask is correctly keyed to the virus in question. And I think that points to the interdisciplinarity of these types of works. And I'm sure the NSF is thinking that way too.
Yeah, obviously we don't want people to be inhaling anything. We don't think inhaling detoxifying agents will clean your lungs either.
Good point. We don't want to, yeah, you've got to be careful what you put on these things as well. So do you have any final thoughts on sort of science in the age of COVID? I mean, how, you know, are there things, you know, you would advise me as dean in thinking about how does the science enterprise at Northwestern succeed at this challenging moment? And do you see any dangers or hope for optimism about the science enterprise, which is challenging because it requires so many people in spaces, right? I mean, that's why we opened up early, because it doesn't work unless you have people in laboratories, etc.
No, I agree with you, but I also think efficiency and being able to think about what do you want to do when you come to the lab and do it is very important. Mm-hmm. What do I mean by that? We've been working in shifts, and my students can accomplish what they accomplish in 6 or 6.5 hour shift as much as maybe their previous 9-10 hour shifts. Why is that? Because if you think about what do you want to tackle the next morning and come with your to-do list and come and execute, then you'll be in your, you could be very efficient if you don't go check your email, don't go on your Twitter and Facebook, wait until you get home and do these non-essential matters. Write your manuscripts at home, check your emails at home, do your meetings over Zoom. They've been fantastic. So in that regard, if you really put an honest to God 6 hours of your work in science and do it efficiently, it's just as good as your full day, because your full day wasn't 6 hours of science.
Well, that's something we all can learn from. So thank you for those words. And I will say again, I think this notion of predictive experimentation is really interesting. If you know exactly, sort of, if you narrow what you need to do and you do it, I think we can be much more efficient and effective with our science. So
I agree with you. And at Northwestern, we are really set up between, you know, the Weinberg College and McCormick, start this collaboration, and we have been doing it. We are set up to do this and do it well. And Argonne National Lab just down the street.
Absolutely. So Omar, thank you so much for sharing your research and its application, especially relating to the pandemic, which is of course on all our minds. I'm sure you've given our attendees many things to think about as they return to their lives. Thank you to all of you who attended. It really was, I don't know, I'm finding this, even though I don't see you, I'm glad you're part of our community. So with that, I hope you join us next time. We're going to continue offering these virtual conversations. And thank you for all of your support of Weinberg College Northwestern. It's you who make the research like this possible. So until next time, thank you, Omar. Thank you all those who helped set this up, and thank you to everyone who participated.
Thank you, Adrian, very much. And thank you to our supporters, to our alumni for attending today. Thank you so much.